Okay. Hello everyone. I'm Feifan Li from Dalian University of Technology. I will share with you the work I completed during my internship at LinkedIn, Dynamic Intent Guided Meta Network for differentiated user engagement forecasting in online professional social platforms. I will introduce our work from the following 5 parts. The first part is introduction. User engagement measures how often and how long users interact with your website or application, which can reflect how much value users get from your website or application. Accurate user engagement forecasting is one of the core technologies for developing user interaction strategies, which can help the platform conduct user modeling, understand user needs, and provide personalized service. Here is a formal definition of the user engagement prediction task. For any user, given users' microscopic features, session sequence, and the latest platform delivery message in the past period, forecasting user engagement trend in the next period can be formulated as follows, where T is the number of the sessions, YU is the user engagement trend label, and theta is the parameter we need to learn. The motivation of our work is mainly from the following points. Real-world users often exhibit different behaviors in online social platforms, leading to diverse engagement patterns. A major reason for the differences in user engagement pattern is that users have different intents, as shown in this figure. For instance, some users tend to look for jobs recently, and they will frequently visit LinkedIn to seek and apply for jobs, increasing their engagement level rapidly in a period. Differentiated user engagement modeling can be more accurate. User intents can be signals to differentiate user engagement patterns. However, user intents are usually not directly observable, and it may change over time. As shown in this figure below, for example, some users initially use LinkedIn to look for jobs, and when they finish looking for jobs, they may use LinkedIn to view industry news. Explicitly modeling dynamic user intent is vital, which can help the platform understand user recent intents to increase user engagement. In this work, our contributions can be summarized as follows. First, we find that user intent can be beneficial for differentiated user engagement forecasting in online professional social platforms. Second, we develop a dynamic intent-guided meta network, which explicitly model user intents evolution over time and leverage intent-guided attention mechanism to adjust model parameters for differentiated user engagement modeling and forecasting. Third, extensive experiments on anonymous data from LinkedIn shows the effectiveness of our proposed method. The next part is user intent mining. In this part, I will introduce how to perform user intent mining and show the basic user intents we obtain from the data mining. The user's intents are usually not directly observed and exist implicitly in users' consciousness. It's difficult for us to collect many user behavior samples with user intent labels. So using unsupervised method for user intent mining is a more feasible option. The user's behaviors on the platform can be abstracted as events for collection. We collect 10 major event types on the platform, as shown in the table below. These 10 events can completely cover users' activities on the platform. As shown in this figure, initiatively, the user's intents influence the user's behaviors, and the user's behaviors constitute the set of events in the session. This process is like generating documents with an unsupervised topic model LDA. We treat each session as a document and each event type as a word, then perform LDA to mine basic user intents on 6 million anonymous user session data. We adopt perplexity as the evaluation metric to search for the optimal intent number from 2 to 10. When the number of intents equals 7, the LDA model has the latest perplexity. These 10 topics can be regarded as these 7 topics can be regarded as 7 basic user intents, each of which is composed of events with different weights as shown in the figure below. The meaning of each intent can be expanded by the top weight events that make up them. For example, we can find that the 2 events with top weight making up intent 1 are people you may know and profile view, indicating that the users want to expand their connections on LinkedIn. The next part is our model, dynamic intent guided meta network. As shown in this figure, our model consists of 3 main components: a behavior evolution layer, an intent evolution layer, and a meta predictor. For each session, we represent it by connecting the session context feature and the session event frequency. We take session context features and the session event frequency as the input of the session LSTM unit at each time step, and take the last time step output of the session LSTM as the representation of the user behavior feature in the past period. Given a session's frequent event frequency and the basic user intents obtained by LDA in the intent mining stage, we can infer user intent during this session. We take each session's intent representation as the input of intent LSTM unit at each time step, and take the intent LSTM's last time step output to represent the user's dynamic intent over past period. Meta predictor contains a meta network and multiple staked fully connected layers with dynamic parameters. The left figure shows how the else fully connected layers with dynamic parameters transforms the input feature to the output feature. In order to reduce redundant information in the else fully connected layers with dynamic parameters, we use an orthogonal regularization term. The right figure shows how the meta network adjusts the parameters in the else fully connected layers with dynamic parameters. We choose cross entropy as the classification loss function. After adding the regularization term for the parameters of the meta predictor, we obtain the final loss function L equals to LC at beta multiply LR, where beta is a hyperparameter that traces off classification loss LC and the regularization term LR. We adopt an end-to-end learning strategy and use error backpropagation to train our proposed model. The next part is the experiments. We conduct experiments on real-world anonymous user data of 4 weeks from LinkedIn. The user engagement trend label is obtained by comparing the user engagement in the first 2 weeks and the following 2 weeks. For the day level task, we adopt macro F1 score as the evaluation metric. For the session level task, AU ROC is adopted as our metric. Firstly, we want to know that can Digman outperform state-of-the-art baselines in user engagement forecasting tasks at different granularities. As shown in this table, we can find that Digman performs best on both day level and session level user engagement prediction tasks. Compared with the fully connected layers, with dynamic parameters used in Digman increase the learnable parameters. So we wonder that does Digman perform better than a network with static parameters and a similar number of parameters? As you can see in this table, we can find that Digman with dynamic parameters outperforms Digman with static parameters in 2 tasks. We also do some ablation study. First, we want to know that how does each part in Digman affect the performance. We use MLP with 2 hidden layers as a predictor to investigate the effectiveness of various components in our model. As shown in this figure, we can find that simultaneously using the user's microscopic features, platform deliver message, session features, and intent features can achieve the best results. Second, we wonder that is dynamic user intent a good signal to differentiate diverse user engagement patterns? As shown in this figure, we find that using intent as a parameter adjustment signal performs best. We conduct the hyperparameter sensitivity study on the session level user engagement prediction task. These 3 figures show the impact of hyperparameters on model performance in Digman. We also do some further analysis to Digman. Firstly, we want to know that what about the impact of using other methods to obtain user dynamic intent representation on Digman performance. We replace the similarity computation operation with player LDA intents in Digman with an end-to-end learning strategy. As shown in this table, we can find that introduce basic player user intents obtained by LDA to my user intents in Digman performs better than directly learning the implicit intent representation. There are usually 2 ways to implement dynamic parameters. One is to dynamic adjust the model parameters, and the other is to generate the model parameters directly. We wonder that what's the influence of different methods to implement dynamic parameters on the prediction effect of Digman. As shown in this table, we can observe that directly generating parameters of fully connected layers with dynamic parameters usually requires a meta network with more parameters, which is prone to overfitting and reduce the model's generalization ability. In the end, we wonder that can Digman learn interpretable user dynamic intent representations? We use PCA to reduce the dimension of dynamic user intent representation from 32 to 3 and 2. In the test dataset of session level user engagement forecasting task, the label of each sample is the user's most frequent intent in the past 2 weeks. As shown in this figure, we can find that intent evolution layer can layer meaningful and discriminative user dynamic intent representation. And the last part is conclusions. In this work, we use LDA on user session data to mine basic user intents. Meanwhile, we propose a dynamic intent guiding meta network to explicitly model user intent evolution over time and perform differentiated user engagement forecasting. Experiments on the real-world data set from LinkedIn demonstrate the effectiveness of our method. That's all. Thanks for your listening.